All right, welcome to the video here, 11.4. It's limits at infinity and limits of sequences. We're going to go ahead and take a look at some more definitions with limits and have some specific procedures to follow. Here's what we've got. If f is a function and L1 and L2 are the real numbers, then the limit as x approaches negative infinity of the function is equal to L1, and the limit as x approaches, see this is positive infinity, this is negative infinity, it equals L2. This would denote the limit at infinity. So right here you can see the symbols that we're going to be using for negative infinity and then to positive infinity. So we have some things that will follow. This is just how we read the notation. The limit of f of x as x approaches negative infinity is L1, and the limit of f of x as x approaches positive infinity is L2. It's just the way that we read the mathematical statements. To evaluate the limits of infinity, we need to consider here our expressions. If r is a positive real number, so if we have a function here, 1 over x to some positive real number, then the limit as x approaches infinity, so as x gets really, really large, this expression 1 over a large number will slowly approach 0. The same is considered here in this example. So the limit as x approaches positive infinity of f of x, 1 over x squared, this is equal to 0. So this is what this evaluating the limit here tells us about going to infinity. And if x to the r is denoted by x being smaller than 0, in other words, going to negative infinity, again, if I substitute really, really, really small numbers in here, the function still approaches 0. So you can see going both positive infinity here and negative infinity, the result of these types of expression, the limit is equal to 0. So giving us this example right here, what I would do is I would need to take the limit as x approaches infinity. I'm going to go ahead and look at one part at a time. So 1 over x to the third plus the limit as x goes to infinity of 5x over x to the third and minus 3, or minus the limit as x approaches infinity of 3x to the third over x to the third. Well, what I can do with each one of these statements, so I purposefully separated these into 3 fractions, and I'm finding the limit of each one of them. Well, the limit of the first one is 0. The limit of the second one, see I can cross out one of these x's, this becomes 5 over x squared, it is also 0. On the last one, I can cross off the x to the thirds, so the limit as x approaches infinity of 3 is just 3, so minus 3. So my solution to this is negative 3. The limit of this expression is negative 3. And we can find it by separating into 3 separate limits and evaluating. Now we do have some rules that we can follow. If f of x is a rational function and the limit of f is taken as x approaches either positive infinity or negative infinity, then the 3 rules exist. First rule, when the degree of the numerator is less than the degree of the denominator, so when n is less than d, these are the degrees, then the limit is 0. When n is equal to d, then it's the n over d ratio, just like when we did asymptotes. And finally, when the degree n is greater than the denominator, the limit does not exist. So we can just follow these rules now. Now I know you don't have any examples currently right now in your packet, but we are going to run through these 3 examples, finding the limit of the expression. All right, well, on top here I have 5x squared minus 15x. On bottom I have 2x. So what we need to do is we just need to compare the degrees. The degree on top here is 2. The degree on bottom is 1. So the limit does not exist. It's larger on top than it is on bottom. Because 2 is greater than 1, it follows this pattern. All right, here I've got the degree is 3 on top, the degree is 4 on bottom, so 3 is less than 4, and that concludes that the limit equals 0. Here the limit is 2, the limit is 2, so they are the same. I do -6 over 3 as a ratio, so the limit is -2. This is how these rules work. All right, for a couple seconds here, we're going to look at just what sequences are. The definition of a sequence is a list of numbers. I'm just going to give you an example, like 1, -1/2, 1/6, -1/24, 120th, and so on. Those are sequences. I guess that's listed right here. I didn't even see it. All right, so we've got ways to describe sequences, and within sequences we're able to use limits. The first description that we have is for a sequence whose nth term, the nth term is a sub n, as n increases without bound, so it's going to infinity. If the terms of the sequence get closer and closer to a particular value L, it is said to converge. So this is like it converges to like how we describe limits. Limits converge to a number. You can see this is slowly going to the number 2. All right, for a sequence that does not converge, in other words, there's no relationship between the numbers, in fact, you can see here it bounces back and forth like it's oscillating, then this is to say that it diverges. So there wouldn't be a limit in this case. Limits of sequences. Let f be a function of real variables. Limit as x approaches infinity of a function equals L. If a sub n is a sequence such that f of n is equal to a sub n, so basically we're saying that this is a sequence, for every positive integer n, the limit as x approaches infinity of the function is also equal to some number. Okay? So we can use sequences and follow these same rules that we've been applying before. All right, find the limit of the sequence. I'm going to show you this one kind of in long form here, but what I'm able to do is I'm able to, let's FOIL the top, so this is 4n squared minus 1n minus 12n is minus 13n. And then it's plus 3 over negative n to the second minus 3n plus 4. Well, these are also just polynomials, so the limit as n approaches infinity. What we can do is we can just compare their degrees. These are just polynomials top and bottom, so the degrees are exactly the same, which means we're going to take the ratio of the coefficients, so it's 4 to -1, which equals -4. That is the result of my limit. In example 3 here, it's already kind of expanded out in the form that we need, so we're comparing the degrees. It's degree of 1 compared to degree of 1. They're the same. Actually, it looks like you guys have a squared here. Let's go ahead and insert that. Degree of 1 on top and a degree of 2 on the bottom. So since this is less than, so 1 is less than 2, this concludes that the limit is equal to 0. And the last one here. Let's go. It looks like I skipped example 3 here. This is example 4 with the n here squared, and then let's just use this as example 1, or the one before that, example 3. So again, your degrees are the same, and so you can just do the 2 to 1, which is 2. All right, now the last problem, if we change the degrees here, so 3 compared to 2, since it's bigger, this concludes that the limit does not exist. And finally here, this is your assignment for the sequences and limits going to infinity.